Hi, welcome to another Cold Fusion video. In this video, we'll take a look at a new type of computing that is set to rival the legendary quantum computer. Let's get straight into it, but first with a bit of background understanding. From phones and tablets to PCs and gaming consoles to supercomputers and smartwatches, computers are everywhere, and you're using one right now. The thing is, all of these types of computers function the same way. These computers use machine language fundamentally composed of ones and zeros to tell the computer what to do. Like a written language, the computer reads word by word or instruction set by instruction set until it understands what to do. It then executes it and moves on to the next step. We call this kind of computer a classical computer. So you might be asking, if my computer can only do one task at a time, how am I running multiple things at once? Well, in basic terms, a computer's CPU is actually still doing one thing at a time or one instruction set at a time, but switching between them really quickly, roughly 2.5 billion times a second for a 2.5 GHz single-core, single-threaded CPU. So it actually just seems like it's doing a lot of things at once. Okay, so that's all fine for running software and things of that sort, but what if the requirements for your use were much more than that? What if you needed vastly more computing horsepower, the kind that allows you to solve complex equations with almost no bounds? Things like cryptography, or complex simulations of things within our world, advanced mathematical models, or just many other applications that we couldn't even dream of today. These kind of problems can be described and categorized as taking exponentially more time to solve with increasing complexity. Classical computers can't do such things very well. The closest thing that we've gotten to is many classical computers slapped together and given the title of a supercomputer. What we need is a computer that can actually solve many problems at the same time. What we need is something called a parallel computer. Alright, so you might be thinking, look, I've heard of this parallel computing thing before, wasn't that what quantum computers were supposed to do? This is correct. However, the researchers in the groundbreaking experiment I'm about to show you state that the quantum computer hasn't been proved to be practical from a fabrication and operational perspective. For example, a quantum computer has to be very close to absolute zero in temperature to even function. These hurdles may be overcome in the future, but for now, there needs to be a better solution. This is where the Biocomputer comes in, of which a brand new feasible solution has just been discovered at Lund University in Sweden. The results have been published in the Proceedings of the National Academy of Sciences. The biocomputing approach uses less than 1% of the energy used by current electronic transistors. The result could see the power of today's supercomputers fit into the form factor of a laptop without absurd amounts of power and heat.
Most of you know that nano means very, very small. I'd like to start by just saying how small. If you imagine you take the whole Earth and reduce it enough to become as large as a football, so that's about 50 million times smaller. And then you imagine you do the same thing one more time. You take the football and take it down another 20 or 50 million times. Then you're at the size of what you call a nanoparticle, something that is on the size range of a few thousand atoms or so, a ball of material. Now, why are we interested in this? The main reason, sometimes the reason is that not making things small, that's just the point. So for example, if you try to build faster and more powerful computers, that's what you want. You want to make smaller transistors so that you can pack many of them into a small space, they can talk quickly to each other, and that's the whole point.
So what exactly is the solution? As it turns out, the solution has been around for a very long time in the form of a protein called myosin, part of our muscle tissue. You're actually using myosin right now in your eyes to watch this video. Myosin can be thought of as tiny molecular motors converting chemical energy into mechanical energy. The Swedish biocomputer uses the myosin to guide protein filaments along artificial paths. Researcher Heiner Linke explains, quote, "In simple terms, it involves building a network of nano-based channels that give specific traffic regulations for protein filaments. The solution in the network corresponds to the answer of a mathematical question, and many molecules can find their way through the network at the same time." End quote. So rather than having bulky computers working in tandem, performing multiple simultaneous computations, you have a nanoscale molecular motor doing the same thing. This means much smaller and more powerful computers. This biocomputer system is much easier and less expensive to build than a quantum computer, mainly because some of the crucial components that are found in this computer are found in nature. The research team say that the biocomputers are likely to be a decade away from production. Here's another quote from the researcher Linke. Quote, "The fact that the molecules are very cheap and that we have now shown that the biocomputer's calculations work leads us to believe that biocomputers have the prerequisites for practical use within 10 years. The research team also states that existing programming algorithms can be used on this system with some optimization. Okay, so we're almost at the end of the video, but let's quickly look at the system in action. You're looking at it right now. The numbers at the bottom represent solved solutions to an equation. As you can see, the system is finding many solutions at the same time. So of course, at the moment, this system looks a little slow and rudimentary, but this study was just a proof of concept showing that the idea is sound, allowing researchers to have enough evidence to foresee this being a viable alternative to quantum computers. Putting it another way, this can be seen as a Wright brothers moment in parallel computing, much like comparing that first measly 450-meter flight that eventually gave the feasible path for all modern aircraft. So, what can we make of all of this? While quantum computing may be the holy grail for the long run, replacing the operating realm of supercomputers, this proof of concept of a practical, easy to manufacture, low energy, low cost parallel computing system may mean that our desktops and future laptops, and even possibly smartphones, could see the power of what we call a supercomputer today. Ultimately, only time will tell if this method truly becomes all that the scientists and researchers say it will, but regardless, it's going to be an interesting decade. For a final further thought, combining the former with new scientific efforts on graphene computing, in which graphene transistors are already clocking 427 GHz, it looks like Moore's law could happily live on for a while yet. Anyway, that's the end of the video. Thanks for watching, guys. Hopefully you could take something away from that. Feel free to give this video a thumbs up if you liked it. Subscribe if you're new, definitely do that. This has been Dagogo, you've been watching Cold Fusion. Cheers guys, have a good one, and I'll catch you again soon for the next video.
Cold Fusion. It's new thinking.